If the moon vanished tomorrow, the oceans wouldn't just look different. They'd sound different. The rhythmic heartbeat of the tides, the ancient pulse that has shaped coastlines for billions of years, would fall silent. But here's the strange part. The moon isn't actually pulling the ocean in the way most people think. In fact, the real reason water moves the way it does is stranger, more delicate, and more beautiful than a simple tug from above. Tonight, let's slow down and drift into the hidden story of how the moon moves the sea, and why that connection may be the most poetic dance in our entire solar system. Hello and welcome to the Sleepy Physicist. I'm so glad you're here. Whether you're settling into bed, curling up on the couch, or just trying to wind down after a long day of wrestling with gravity and deadlines, you've come to the right place. This is a quiet little corner of the internet where physics gets soft-spoken and curiosity puts on pajamas. Tonight, we're diving into one of the most mesmerizing dances in our solar system, the invisible choreography between the moon and our oceans, and how a celestial body nearly 250,000 miles away manages to move trillions of gallons of water twice a day. It's a story filled with invisible forces, ancient mathematics, and the kind of cosmic precision that makes you wonder if the universe has been planning this all along. Now, I do hope this video isn't so fascinating that it keeps you wide awake. But hey, if it does, at least you'll be learning something genuinely extraordinary about the world beneath your feet before we begin. If you enjoy these gentle journeys through the mysteries of physics, and you'd like to help this sleepy little channel grow, I'd be ever so grateful if you tapped the like button, subscribed, or even just left a comment telling me where in the world you're watching from, and what time the tide is, where you are. All right, take a deep breath, settle in, and let's begin our quiet voyage into the hidden mechanics of the tides. Here's something that might surprise you every single day without fail. Our planet experiences something that would seem utterly impossible if you didn't know the science behind it twice daily. The entire ocean rises and falls in a rhythm so precise you could set your watch by it. Not just a little bit either. We're talking about vertical movements of water that can reach 17 meters in some places. That's higher than a 5-story building. Imagine if twice a day, every swimming pool on Earth suddenly rose up to the level of the roof and then gently fell back down again, all in perfect synchronization. Now imagine that this happens not because of pumps or machines or human intervention, but because of a rock floating in space nearly 400,000 kilometers away. This is the mystery of tides, and it's far more elegant and surprising than most people realize. Because here's the thing that puzzles so many when they first learn about tides. If the moon's gravity is pulling on our oceans, why do we get high tides on both sides of the Earth at the same time? Shouldn't there only be one bulge of water on the side facing the moon? It seems like the ocean should be reaching toward our celestial neighbor like a cosmic embrace. But instead, we get this strange symmetrical dance with water rising on opposite sides of the planet simultaneously. The answer to this puzzle lies in understanding something that Newton himself grappled with in 1687 when he first tried to explain the tides. It's not just about gravity pulling. It's about gravity pulling differently. And that difference, my friends, is where the magic happens. Let me paint you a picture. Imagine you're holding a ball of soft clay and someone is gently pulling on one side of it. The clay doesn't just move as a solid chunk toward the pull. Instead, it stretches the side closest to. The pull gets drawn out, while the side farthest away gets left behind, creating an elongated shape with bulges on both ends. This is essentially what happens to our planet every single day, except instead of clay, we're talking about an entire world covered in water. And instead of someone pulling by hand, we're talking about the moon's gravity reaching across the void of space. The mathematics behind this phenomenon is breathtakingly elegant, and it all comes down to something called the inverse cube law. While gravity itself follows an inverse square relationship, meaning it gets weaker with the square of the distance, tidal forces follow an inverse cube relationship. They weaken with the cube of the distance. This might sound like a small detail, but it's the key to everything. Let me put this in perspective. The sun is 27 million times more massive than the moon, and its gravitational pull on Earth is 177 times stronger than the moon's pull. So why doesn't the sun dominate our tides? The answer is distance. The sun sits about 390 times farther from Earth than the moon does. And because tidal forces depend on the cube of distance, this means the sun's tide generating force is reduced by 390 cubed, or about 59 million times. When you do the math, the sun's tidal influence ends up being only about half as strong as the moon's. This is why when people ask whether the full moon really affects human behavior or ocean life, the answer is both simpler and more complex than they expect. The moon absolutely affects our planet in measurable ways, but not because of mysterious lunar energy. It's because of precise mathematical relationships that govern how gravity works across space. Now here's where things get beautifully counterintuitive. The tidal bulges on Earth don't actually line up directly with where the moon is in the sky. If you went to the beach and waited for the moon to be directly overhead, you wouldn't necessarily see high tide. Why? Because Earth is spinning much faster than the moon is orbiting our planet. Rotates once every 24 hours, while the moon takes about 28 days to complete its orbit. This creates a fascinating cosmic lag. The tidal bulges try to stay aligned with the moon, but Earth's rotation drags them along like a cosmic friction. The result is that high tides don't occur when the moon is directly above you. They occur roughly when the moon is at a 45-degree angle in the sky. This mismatch between the moon's position and the tide's timing is actually evidence of something profound happening to our planet. You see, every single day the tides are stealing energy from Earth's rotation through a process called tidal friction, as our planet spins beneath these bulges of water. Friction converts some of Earth's rotational energy into heat. This might sound insignificant, but over geological time it adds up dramatically. Earth's day is getting longer at a rate of about 2.3 milliseconds per century, and all that stolen energy has to go somewhere. It gets transferred to the moon, causing our celestial companion to slowly spiral outward away from us. This means that billions of years ago, the moon was much closer to Earth and our days were much shorter. Ancient coral fossils from 400 million years ago show growth rings that tell us a day back then was only about 22 hours long, and there were over 400 days in a year. Go back even further to 900 million years ago, and the day was just 18 hours long, with the moon looming much larger in the sky. The beauty of this system extends far beyond just moving water around. Tidal forces affect the entire solid Earth, causing our planet's surface to rise and fall by about 10 centimeters twice daily. Most of us never notice this because we're riding along with the land as it gently flexes, but sensitive instruments can measure it. And it's happening right now beneath your feet. But the real magic of tides becomes apparent when you look at places where geography amplifies these cosmic forces. Take the Bay of Fundy in Canada, where the natural period of water sloshing back and forth in the bay happens to match almost exactly with the 12.5-hour tidal cycle. This creates what physicists call resonance, like pushing a child on a swing at just the right moment. The small push of the tides gets amplified into something spectacular. During spring tides in the Bay of Fundy, the difference between high and low water can reach 17 meters. Imagine standing on a beach and watching the water level drop the height of a 5-story building, then rise back up again, all in the space of about 6 hours. The amount of water moving in and out of this bay during each tidal cycle is staggering more water than flows through all the rivers of the world, combined in the same time period, about 110 billion tons of water, twice daily. This is what happens when the precise clockwork of celestial mechanics meets the chaotic geography of our planet. The moon provides the driving force, but the shape of coastlines, bays, and ocean basins determines how that force gets expressed. Some places experience barely noticeable tides, while others, like the Bay of Fundy, become theaters for one of nature's most dramatic daily performances. What fascinates me most about tides is how they reveal the interconnectedness of everything. The moon tugs on every drop of water in every ocean lake and even the water in your body. But it also pulls on the solid rock beneath your feet, the air you breathe, and every atom that makes up our planet. The reason we notice it most in the oceans is simply that water can flow freely, responding to forces that solid rock can only acknowledge with the tiniest of flexes. And this cosmic dance has been going on for billions of years, long before the first life crawled out of tidal pools, long before humans looked up at the moon and wondered about its influence. The gravitational conversation between Earth and Moon has been shaping our world. Tides may have even played a crucial role in the evolution of life, providing the regular rhythm of wet and dry that could have helped early organisms make the transition from sea to land. There's something deeply humbling about realizing that twice each day the entire ocean responds to the gentle pull of our celestial neighbor. It's a reminder that we live in a universe where distant objects can reach across the vacuum of space and move mountains of water with nothing but the curvature of space-time itself. As we continue this journey into the hidden mechanics of tides, we'll explore how ancient mathematicians first cracked the code of these patterns, how modern science has revealed the intricate details of tidal friction and energy transfer, and why understanding tides opens a window into some of the most fundamental forces that govern our universe. But for now, just think about this. The next time you're near any body of water, whether it's the ocean, a lake, or even a puddle after rain, that water is responding, however subtly, to the moon's presence. It's participating in a cosmic conversation that's been going on since the formation of our solar system and will continue long after we're gone. The moon is out there right now as you listen to this, quietly orchestrating the movement of trillions of gallons of water with mathematical precision that would make the most sophisticated computer seem clumsy by comparison. And somehow in this vast universe filled with violent supernovas, black holes, and cosmic collisions, we get to witness this gentle daily dance between worlds. Now let's step into the workshop of the cosmos and examine the actual machinery that makes this daily miracle possible. Because when Newton first sat down to work out the mathematics of tides in 1687, he discovered something that would forever change how we think about forces acting across empty space. The key insight that unlocks the mystery of tides isn't just that the moon pulls on Earth's water. It's that the moon pulls on different parts of Earth with different strengths. And here's where the mathematics becomes poetry. Imagine you're standing on the side of Earth closest to the moon. At this moment, you're about 4,000 miles closer to our celestial neighbor than someone standing at Earth's center, and you're 8,000 miles closer than someone on the far side of the planet. Now, 8,000 miles might seem insignificant when you're talking about a 250,000-mile journey, but gravity is exquisitely sensitive to distance. Remember that inverse square law. The gravitational force between two objects decreases with the square of the distance between them. So if you double the distance, you get 1/4 the force. But tidal forces follow an even steeper relationship. They decrease with the cube of the distance. This means that your body standing on the moon-facing side of Earth experiences a gravitational pull toward the moon that's measurably stronger than the pull felt by Earth's center. And Earth's center feels a stronger pull than the far side. This difference in gravitational strength across Earth's diameter is what we call the tidal force. And it's this difference that stretches our planet like taffy. But here's where it gets wonderfully strange. The water on the side of Earth facing the moon gets pulled toward our celestial companion more strongly than Earth itself does. So it bulges outward, forming what we see as high tide. But on the far side of Earth, something equally fascinating happens. The planet itself gets pulled toward the moon more strongly than the water on that far side does, which means Earth essentially gets pulled out from under that water, leaving it behind to form another bulge. It's as if you grabbed a water balloon by one side. The water nearest your hand would bulge toward you, but the water on the far side would also bulge outward as the balloon itself got pulled away from it. This is why we get two high tides, roughly 12 hours apart as Earth rotates. We pass through both bulges. Each day, the mathematical elegance of this system becomes even more beautiful when you realize that these aren't just random bulges of water. They're standing waves that maintain their orientation relative to the moon while Earth spins beneath them. Imagine a cosmic lighthouse with its beam always pointing toward the moon. As our planet rotates, different coastlines pass through this beam, experiencing high tide. But the real world isn't quite so simple as our mathematical models suggest. If Earth were a perfect sphere covered in a uniform ocean, the tidal bulges would be symmetrical and predictable. But our planet is anything but uniform. We have continents that block the flow of water-ocean basins of varying depths, underwater mountain ranges, and countless other geographic features that complicate the picture. This is where local geography becomes a cosmic amplifier. Take the Mediterranean Sea, for example, because it's almost completely enclosed by land. The Mediterranean experiences very small tides, usually just a few centimeters. The water simply doesn't have room to slosh back and forth in response to the moon's pull contrast. This with the Bay of Fundy, where the shape of the coastline creates a natural funnel that concentrates tidal energy. In the Bay of Fundy, something remarkable happens. The natural period of oscillation for water in the bay is about 12.5 hours, which is almost exactly the same as the time between successive high tides. This coincidence creates what physicists call resonance, and just like pushing a child on a swing at exactly the right moment, the result is amplification beyond what you might expect. During the highest spring tides, when the sun and moon align to reinforce each other's gravitational pull, the Bay of Fundy becomes a theater for one of Earth's most dramatic daily performances. The water doesn't just rise and fall, it surges and retreats with tremendous power, carrying with it fishing boats that might be sitting on the sea floor at low tide, only to be floating 30 feet above that same spot. 6 hours later, the sheer volume of water involved is staggering. During each tidal cycle, approximately 110 billion tons of water flows into and out of the bay. That's more water than flows through all the rivers on Earth, combined in the same time period, and this happens twice every single day, powered by nothing more than the gentle gravitational tug of our moon. But tides aren't just about moving water around, they're also about moving energy, and this is where the story becomes even more fascinating. Every time water flows over the sea floor, or crashes against a coastline. Some of the tidal energy gets converted to heat through friction. This might seem like a tiny effect, but when you multiply it across all the world's oceans, the numbers become astronomical. Scientists estimate that tidal friction dissipates about 3.7 terawatts of power continuously. That's roughly equivalent to the output of 3,700 nuclear power plants, running at full capacity 24 hours a day. This energy has to come from somewhere, and that somewhere is Earth's rotation. Our planet is gradually slowing down as the tides steal rotational energy and convert it to heat. The evidence for this cosmic energy transfer is written in the rocks themselves. Ancient tidal rhythmites layers of sediment deposited by prehistoric tides show us that 600 million years ago, a day on Earth lasted only about 21 hours. As we go further back in time, the days get even shorter, and the moon appears larger in the sky because it was much closer to Earth. This brings us to one of the most beautiful aspects of the tidal story. The energy stolen from Earth's rotation doesn't just disappear. It gets transferred to the moon, causing our celestial companion to gradually spiral outward. Every year, the moon moves about 3.8 centimeters farther from Earth, roughly the same rate at which your fingernails grow. This slow cosmic waltz has been going on for over 4 billion years, and it will continue for billions more, but not forever. Eventually, Earth's rotation will slow down so much that the same side of our planet will always face the moon, just as the same side of the moon always faces Earth. When this happens in about 50 billion years, Earth days will be 47 times longer than they are now, and the moon will take 47 of our current days to orbit Earth. The mathematical precision of this system is breathtaking when you consider that it all emerges from the simple inverse square law of gravity. Yet the consequences ripple through time, affecting everything from the length of our days to the evolution of life itself. Some scientists think tides may have played a crucial role in helping early life forms transition from ocean to land by creating regular cycles of wet and dry conditions in coastal areas. There's something profoundly moving about realizing that the same forces that create the gentle lapping of waves on a beach also govern the orbital mechanics of planets around distant stars. Tidal forces aren't unique to Earth and Moon. They operate wherever gravitational fields vary across space. From the volcanic activity on Jupiter's moon, Io powered by tidal heating, to the spectacular spaghettification of matter falling into black holes. Even now, as you listen to these words, the solid ground beneath you is rising and falling by about 10 centimeters, twice daily in response to the moon's pull. You can't feel it, because you're moving along with the Earth, but sensitive instruments can measure this terrestrial tide with remarkable precision. It's a reminder that we live on a dynamic planet that flexes and breathes in response to cosmic forces. The study of tides has also revealed something unexpected about the nature of time itself, because tidal friction is gradually slowing Earth's rotation. Atomic clocks, which keep time based on the vibration of atoms, gradually drift out of sync with astronomical time based on Earth's rotation. This has forced scientists to occasionally add leap seconds to our official timekeeping systems to keep them aligned with the actual rotation of our planet. In a very real sense, the moon is editing our calendar 1 millisecond at a time, and this editing process leaves traces everywhere we look, from the growth rings in ancient corals that record the changing length of days to the precise orbital mechanics of artificial satellites that must account for the gradual changes in Earth's rotation. Perhaps most remarkably, the mathematical tools developed to understand tides have found applications far beyond oceanography. The same principles that explain why water bulges on both sides of Earth help us understand how binary star systems evolve, how galaxies interact gravitationally, and even how quantum fields behave in curved space-time. The inverse cube law that governs tidal forces appears throughout physics wherever we encounter systems where the gradient of a force matters more than the force itself, from the way atoms bond together to form molecules, to the way dark matter sculpts the large-scale structure of the universe. Tidal effects are everywhere once you know how to look for them. This universality hints at something deeper about the nature of physical law. The same mathematical relationships that Newton discovered while puzzling over the twice-daily rhythm of ocean tides turn out to describe phenomena across every scale of the cosmos, from the subatomic to the intergalactic. It's as if the universe has a fundamental preference for certain mathematical forms, certain ways of organizing matter and energy. And yet, for all our mathematical sophistication, there remains something almost mystical about standing on a beach at twilight, watching the tide come in, knowing that the water rising toward your feet is responding to the gentle pull of that bright disk hanging in the darkening sky. It's one thing to understand the equations, another thing entirely to feel the reality they describe. The next time you find yourself near the ocean, try this little experiment. Arrive about an hour before high tide and simply watch as the water slowly creeps up the beach. If you're patient, you can actually see the tide coming in, not as a dramatic wall of water, but as a gradual, inexorable rise that transforms the entire coastline. The same gravitational conversation that's been going on for billions of years is happening right in front of you. What strikes me most about tides is how they remind us that we live in a connected universe where nothing exists. In isolation, the moon's influence on Earth's oceans is just one thread in a vast web of gravitational relationships that binds together everything from the smallest asteroids to the largest galaxy clusters. Every mass in the universe tugs on every other mass, creating a cosmic symphony of forces that plays out across both space and time. As we continue exploring the hidden science of tides, we'll discover how this ancient rhythm has shaped not just our oceans, but the very evolution of life itself. How the precise timing of tidal cycles may have provided the metronome for biological processes that eventually led to complex organisms and consciousness, and how understanding tides has opened windows into some of the most profound questions in physics about the nature of space-time and gravity. But there's another layer to this story that's even more surprising: the role that tides play in the delicate dance of climate and weather systems across our planet. Now, as fascinating as the mechanics of tidal forces are, there's an entire hidden dimension to this story that most people never consider. The moon's gravitational embrace doesn't just move water around our planet, it actually helps regulate the very climate that makes life possible. And this brings us to one of the most elegant examples of cosmic fine-tuning in our solar system. You see, the same tidal forces that create those dramatic 17-meter swells in the Bay of Fundy also drive something called thermohaline circulation, the great conveyor belt of ocean currents that carries warm water toward the poles and cold water toward the equator. Without this massive circulation system, our planet's climate would be far more extreme, with scorching equatorial regions and frozen polar zones that would make much of Earth uninhabitable. The connection between tides and global climate works like this. As tidal forces push and pull ocean water around the planet, they create mixing between different layers of the sea. Deep, cold water gets churned up toward the surface, while warm surface water gets pushed down into the depths. This vertical mixing is crucial because it distributes heat energy throughout the entire ocean system. But there's more. The rhythm of tidal mixing also affects how much carbon dioxide our oceans can absorb from the atmosphere. When deep, nutrient-rich water gets brought to the surface by tidal action, it feeds microscopic marine organisms called phytoplankton. These tiny creatures consume carbon dioxide and produce oxygen through photosynthesis, acting as a vast biological pump that helps regulate our planet's atmospheric composition. Think about that for a moment. The same moon that lights up your evening sky is helping to maintain the delicate balance of gases that you breathe. Every breath you take has been influenced, however indirectly, by lunar gravity, reaching across 250,000 miles of empty space. This climate connection reveals something profound about how planetary systems evolve. Earth's large moon isn't just unusual in our solar system, it's extraordinarily rare. Most planets either have no moons at all, or they have tiny captured asteroids that exert negligible gravitational influence. But our moon is roughly 1/4 the size of Earth, making it more like a double planet system than a traditional planet-moon pair. This unusual configuration may be no accident. Many scientists now believe that having a large moon like ours is one of the essential ingredients for a planet to develop and maintain complex life. The tidal forces don't just regulate climate. They also help stabilize Earth's axial tilt. Without the moon's gravitational anchor, our planet would wobble chaotically as it orbits the sun, causing wild swings in climate that would make the evolution of complex organisms nearly impossible. Mars offers a cautionary tale here. The red planet has 2 tiny moons, Phobos and Deimos, that are really just captured asteroids. They exert almost no tidal influence, and Mars experiences dramatic changes in its axial tilt over geological time. This instability may be one reason why Mars, despite having liquid water in its ancient past, never developed the kind of stable environment needed for complex life to flourish. But let's return to our own world and dive deeper into the intricate mathematics that governs these tidal relationships. When Newton first worked out his theory of universal gravitation, he struggled with tides for months. The problem seemed deceptively simple at first glance, but the more he examined it, the more complex it became. The breakthrough came when Newton realized that he needed to think about tidal forces not as a single pull, but as the difference between gravitational forces at different points. This insight led him to what we now call the tidal force equation, which shows that tidal acceleration varies not with the inverse square of distance, like regular gravity, but with the inverse cube. This seemingly small mathematical distinction has enormous consequences. It means that tidal forces fall off much more rapidly with distance than gravitational forces do. Double the distance to the moon, and its tidal influence drops to 1/8 of its original strength. This is why the sun, despite being vastly more massive than the moon, produces only about half the tidal force on Earth. The mathematical elegance becomes even more apparent when you consider what happens during spring tides and neap tides. Twice each month, during the new moon and full moon phases, the sun and moon align gravitationally. Their tidal forces don't simply add together, they interfere constructively, creating what mathematicians call superposition. The result is spring tides, where the difference between high and low water reaches its maximum. A week later, during the first and third quarter moon phases, the sun and moon pull at right angles to each other. Now their tidal forces interfere destructively, partially canceling each other out to create neap tides with smaller tidal ranges. This monthly cycle of constructive and destructive interference is like a cosmic demonstration of wave physics playing out in our oceans. But perhaps the most beautiful aspect of tidal mathematics is how it reveals the deep connection between rotation and orbital motion. The same equations that describe how Earth's rotation is slowing down due to tidal friction also predict exactly how the Moon's orbit must be changing in response. It's a perfect example of conservation laws in action. Energy and angular momentum can neither be created nor destroyed, only transferred from one form to another. The energy being drained from Earth's rotation has to go somewhere, and that somewhere is the Moon's orbital energy. As our planet spins more slowly, the Moon spirals outward, gaining potential energy as it climbs to a higher orbit. Eventually, billions of years from now, this process will reach an equilibrium, where Earth always keeps the same face toward the Moon, just as the Moon already keeps the same face toward Earth. This tidal locking is incredibly common throughout the solar system. Most large moons are tidally locked to their planets, and many planets in close orbits around their stars are tidally locked as well. It's gravity's way of creating stability, eliminating the chaotic tumbling that would otherwise occur when two massive objects orbit close to each other. The precision of these tidal calculations is remarkable. Using laser ranging experiments where scientists bounce laser beams off reflectors placed on the Moon by Apollo astronauts, we can measure the Moon's distance to within a few centimeters. These measurements confirm that our celestial companion is indeed receding at exactly the rate predicted by tidal theory, about 3.8 centimeters per year. This level of precision opens up extraordinary possibilities for understanding the early solar system. By working backward from current tidal relationships, scientists can reconstruct what Earth and the Moon were like billions of years ago. The evidence suggests that when the Moon first formed, possibly from debris created by a Mars-sized object colliding with the early Earth, our celestial companion was much closer, perhaps only 15,000 miles away compared to today's 240,000 miles. At that distance, the Moon would have appeared enormous in the sky, roughly 14 times larger than it appears today. The tides would have been stupendous, with water rising and falling by hundreds of meters. Earth's day would have lasted only about 5 hours, and the month would have been just a week long. It must have been a spectacular and terrifying time, with massive tidal bores racing across the landscape twice daily. These extreme early tides may have played a crucial role in jump-starting life on our planet. The constant churning would have created countless tide pools, natural laboratories where organic molecules could concentrate and interact in ways that might not have been possible in the open ocean. The regular wet-dry cycles could have provided the energy gradients needed for the first self-replicating molecules to form. There's even speculation that the rhythm of tides may have influenced the earliest biological clocks. Many marine organisms still time their reproductive cycles to specific tidal phases, suggesting a deep evolutionary connection between lunar cycles and the machinery of life itself. Your own body maintains circadian rhythms that roughly match Earth's rotation period, but there are hints of longer cycles that might echo our planet's ancient relationship with a much closer moon. The story of tides also illustrates something profound about the nature of scientific discovery. Newton's work on tides was some of the most difficult mathematics of his career, requiring him to develop entirely new ways of thinking about forces and motion. Yet the insights he gained from studying ocean tides ended up revolutionizing our understanding of gravity itself. The same mathematical framework that explains why water bulges on both sides of Earth also describes how binary stars spiral into each other, how galaxies merge, and even how ripples in space-time itself propagate outward from colliding black holes. The gravitational waves detected by LIGO interferometers are essentially tidal forces oscillating at incredibly high frequencies, stretching and compressing space itself. This universality of tidal phenomena hints at something deeper about the structure of reality. The mathematics of differential forces, of gradients and curvatures, appears everywhere in physics, from the quantum scale to the cosmic scale. It's as if the universe has a fundamental preference for certain mathematical forms, certain ways of organizing energy and information. Even the human brain seems to resonate with tidal rhythms in unexpected ways. Studies have found correlations between lunar phases and various biological processes, though the mechanisms remain mysterious. Some researchers speculate that our ancestors' intimate connection with tidal cycles for navigation, fishing, and coastal survival may have left subtle imprints in our neural architecture. What strikes me most about tides is how they demonstrate the interconnectedness of everything in our solar system. The same gravitational conversation that moves oceans also affects the solid Earth, the atmosphere, and even the magnetic field generated by our planet's molten core. Tidal forces create currents in Earth's liquid outer core, and these currents help maintain the magnetic dynamo that protects us from harmful solar radiation. Without our magnetic field, Earth's atmosphere would gradually be stripped away by the solar wind, leaving us as barren as Mars. So in a very real sense, the moon's gravitational embrace helps maintain the protective bubble that makes our world habitable. Every time you see the northern lights dancing across the polar sky, you're witnessing the interaction between solar particles and a magnetic field that exists partly because of tidal forces generated by our celestial companion. This brings us to one of the most intriguing questions in astrobiology. How common are Earth-like planets with large moons? As we discover thousands of exoplanets orbiting other stars, we're finding that planetary systems come in a bewildering variety of configurations. Some have hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Others have super-Earths with masses several times our planet's size. But large moons seem to be remarkably rare. Most of the exoplanets we've detected show no signs of having significant lunar companions. This rarity might help explain why complex life appears to be so uncommon in the universe, despite the vast number of potentially habitable worlds. The formation of our own moon was probably a cosmic accident, the result of a catastrophic collision early in Earth's history that just happened to create the right conditions for a stable, large satellite. If that collision had been slightly different in angle, timing, or the mass of the impacting object, we might have ended up with no moon at all, or with a ring system like Saturn's, or with multiple small moons that would provide no tidal stability. This accident may be one of the great filters that determine whether a planet can develop and sustain complex life over geological timescales. Without strong tidal forces to regulate climate, mix the oceans, and stabilize axial tilt, Earth might have remained a world of simple microorganisms, never developing the intricate ecosystems that eventually gave rise to consciousness and curiosity. As we prepare to explore the most dramatic examples of tidal forces in action, from the volcanic fires of Io to the spaghettification zones around black holes, remember that all of these phenomena spring from the same mathematical principles that govern the gentle rise and fall of water on your local beach. The cosmos operates by surprisingly simple rules, but those rules can produce effects of staggering complexity and beauty when they play out across the vast scales of space and time. And nowhere is this more apparent than in the eternal dance between worlds, where gravity reaches across emptiness to move mountains of water with the precision of a Swiss watch. Now let's journey to the edges of our solar system and beyond, to places where tidal forces become so extreme they literally tear matter apart, revealing the true power hidden within these seemingly gentle cosmic caresses. But the true poetry of tidal forces only reveals itself when we venture beyond the gentle rhythms of earthly shores to witness what happens when gravity becomes so intense that it literally reshapes reality itself. Let's take a journey to Jupiter's moon. A world where tidal forces have created something that would seem impossible if we hadn't seen it with our own eyes. A moon that's essentially turned inside out by gravitational stress. Io orbits Jupiter at a distance of about 420,000 kilometers, roughly the same distance that separates Earth from our own moon. But Jupiter is 318 times more massive than Earth, and that makes all the difference. As Io follows its slightly elliptical orbit around the gas giant, the tidal forces stretching and squeezing this unfortunate moon vary in strength, like a cosmic accordion being played by an invisible giant. When Io is closest to Jupiter in its orbit, the tidal bulge reaches its maximum height when it swings farther away. The bulge subsides, but the solid rock and metal that make up Io's interior can't flow as easily as water. This constant flexing generates enormous amounts of heat through friction deep within the moon's interior. Enough heat to melt rock and drive the most volcanically active world in our solar system. Io's surface is constantly being reshaped by sulfur and silicate lava flows that paint the landscape in brilliant yellows, oranges, and reds. Some of these volcanic plumes shoot material hundreds of kilometers into space, creating a thin atmosphere and even feeding particles into Jupiter's radiation belts. What's remarkable is that we can calculate exactly how much heat should be generated by this tidal flexing, using the same mathematical principles that explain our earthly tides. The numbers match the observations, perfectly confirming that we truly understand how gravity works across the vast scales of our solar system. Io is essentially a moon-sized laboratory for studying extreme tidal physics in action. But if we think Io represents the upper limit of tidal destruction, we haven't yet met the true monsters of the gravitational universe. Let's venture much farther from home to encounter objects so dense that their tidal forces can literally pull apart the atoms that make up ordinary matter. Picture a neutron star, a sphere only about 20 kilometers across, but containing more mass than our entire sun, compressed into a volume smaller than Manhattan. These objects are so dense that a teaspoon of neutron star material would weigh about 6 billion tons on Earth. That's roughly the mass of Mount Everest, compressed into something you could hold in your hand. If you somehow had the strength, near a neutron star, tidal forces become so extreme that they reveal the ultimate limits of what matter can endure. If you somehow found yourself falling toward one of these cosmic lighthouses, and will ignore for the moment the lethal radiation that would vaporize you long before tidal effects became relevant. The difference in gravitational pull between your head and your feet would become noticeable at a distance of several hundred kilometers. As you fell closer, this differential force would grow stronger, following that same inverse cube law that governs earthly tides. But now the mathematics takes on a sinister character. The tidal acceleration at your feet would be significantly greater than at your head, stretching your body like a piece of cosmic taffy. Astronomers have coined a delightfully macabre term for this process: spaghettification. The beautiful and terrifying thing about spaghettification is how it demonstrates the ultimate power of differential forces long before the absolute strength of gravity becomes overwhelming. The gradient of the gravitational field begins to tear apart anything that has a finite size. It's a reminder that in physics, the rate of change often matters more than the absolute magnitude. But neutron stars pale in comparison to the true titans of tidal destruction, black holes. These objects represent the ultimate endpoint of gravitational collapse, where matter has been compressed beyond any known limit, creating regions of space-time so curved that even light cannot escape their gravitational embrace. Near a black hole, tidal forces can become so intense that they operate on scales. We can barely comprehend a stellar mass. Black hole, about 10 times the mass of our sun, would begin noticeably stretching a human body at a distance of roughly 600 kilometers from the event horizon. But supermassive black holes, the giants that lurk at the centers of galaxies, can have masses billions of times greater than our sun. Paradoxically, these supermassive monsters are actually gentler in their tidal embrace because their event horizons are so much larger. The tidal forces at the event horizon of a supermassive black hole might be no stronger than what you experience right now. Sitting in Earth's gravitational field, you could theoretically cross the event horizon without being torn apart, though you'd still face the rather significant problem of never being able to return. This reveals something profound about the nature of black holes. They're not cosmic vacuum cleaners sucking up everything in their vicinity. They're simply regions where space-time has been curved so extremely that the geometry itself becomes the prison. The tidal forces that seem so destructive from our perspective are just the natural consequence of following the straightest possible path through curved space-time. When astronomers observe distant galaxies, they sometimes witness spectacular displays called tidal disruption events. These occur when a star wanders too close to the supermassive black hole at the galaxy's center. The tidal forces strip away the star's outer layers, creating brilliant flares of X-ray and optical light that can outshine the entire galaxy for months. These events provide a unique window into the physics of extreme gravity, allowing us to test Einstein's theories of general relativity in regimes that are impossible to recreate on Earth. Every tidal disruption event is essentially a cosmic laboratory where we can watch the fundamental laws of physics play out on scales that dwarf human comprehension. But perhaps the most amazing discovery in recent years has been the detection of gravitational waves, ripples in space-time itself created when massive objects accelerate. These waves are essentially tidal forces propagating at the speed of light, stretching and compressing space as they pass by. When the LIGO detectors first measured gravitational waves from colliding black holes, they were detecting changes in the length of their 4-kilometer arms, smaller than 1/10,000th. The width of a proton. Think about that for a moment. Scientists have built instruments sensitive enough to measure tidal forces oscillating at frequencies of hundreds of hertz, caused by black holes spiraling into each other, billions of light years away. It's as if we've learned to feel the gravitational heartbeat of the universe itself. These gravitational wave detections have opened an entirely new window onto the cosmos, allowing us to witness cosmic events that produce no light at all. We're now routinely observing the collisions of neutron stars and black holes events, so violent they create elements heavier than iron and scatter them across space to eventually become part of new stars and planets. The gold in your jewelry, the platinum in catalytic converters, the uranium in nuclear reactors. All of these elements were likely forged in the tidal maelstrom surrounding colliding neutron stars and then flung across the galaxy by gravitational forces. We're only just beginning to understand. We are quite literally made of stardust that was shaped by tidal forces operating on cosmic scales. As we contemplate these extreme manifestations of gravity's reach, it's worth remembering that the same mathematical principles that describe the gentle lapping of waves on an earthly beach also govern the most violent events in the universe. The inverse cube law that explains why the Bay of Fundy has such dramatic tides also determines how close a star can approach a black hole before being torn apart. This universality of physical law is one of the most beautiful aspects of science. The equations that Newton developed while puzzling over ocean tides have guided spacecraft to the outer planets, helped us discover thousands of exoplanets, and allowed us to detect gravitational waves from the most extreme objects in the cosmos. There's something deeply satisfying about this mathematical unity. It suggests that beneath the apparent chaos and complexity of the universe, there are simple, elegant principles waiting to be discovered, principles that connect the smallest scales to the largest, the most gentle phenomena to the most violent. As we near the end of our journey through the hidden science of tides, let me share one final thought that captures why I find this subject so endlessly fascinating. Every time you watch the tide come in, you're witnessing the same fundamental physics that powers volcanic eruptions on distant moons, creates the spectacular light shows of tidal disruption events, and generates the gravitational waves that carry information about cosmic collisions across billions of years. The moon hanging in your evening sky is engaged in the same gravitational conversation that plays out around black holes and neutron stars throughout the universe. It's participating in a cosmic symphony that began with the first formation of matter in the early universe and will continue until the last black holes evaporate through Hawking radiation. Trillions of years in the future, this perspective transforms something as mundane as a walk on the beach into a profound meditation on our place in the cosmos. Every footprint you leave in the sand is shaped by forces that connect you to the most distant galaxies. Every breath you take happens within a gravitational field that extends infinitely in all directions, linking you to every other piece of matter in the universe. The study of tides teaches us that we live in a deeply interconnected reality where nothing exists in isolation, where the gentle pull of our moon reaches across space to move vast quantities of water, and where the same mathematical principles that govern our local shores also determine the fate of stars around distant black holes. So the next time you find yourself near any body of water, whether it's the vast Pacific Ocean or a small pond in your neighborhood, take a moment to appreciate the invisible forces at work. The water you're looking at is participating in a cosmic dance that connects the smallest scales to the largest, the most ancient past to the far future. Remember that the same gravitational waves that LIGO detects from colliding black holes are passing through your body right now, stretching and compressing your very atoms by amounts smaller than the nucleus, but measurable. Nonetheless, you are quite literally being touched by the most distant and violent events in the universe. Events that happened billions of years ago and whose influence is only now reaching Earth. This is the true hidden science of tides, not just the movement of water on earthly shores, but the revelation that we live in a universe where everything is connected by invisible threads of gravitational influence, where the mathematics of differential forces governs phenomena from the quantum scale to the cosmic scale, and where understanding the gentle rhythm of ocean tides opens doorways to comprehending the most extreme physics in existence. As you drift off to sleep tonight, perhaps you'll dream of cosmic oceans where tidal forces sculpt the very fabric of space-time itself, where black holes and neutron stars dance their gravitational ballet, and where the same moon that pulls at our earthly seas also represents our connection to the vast, beautiful, and mathematically elegant universe that surrounds us. Thank you for joining me on this gentle exploration of forces that reach across the void to move worlds before you go. I'd love to know where you are in the world right now, and whether you can see the moon from wherever you're listening. What phase is it in? And can you imagine the invisible tidal forces it's creating, even as we speak? If this quiet journey through cosmic mechanics has stirred your curiosity, I hope you'll consider subscribing to join our little community of sleepy scientists who find wonder in the hidden workings of reality. And if you'd like to continue exploring the beautiful mathematics that governs our universe, you might enjoy our investigation into how black holes bend light itself, revealing the geometry of space-time in ways that would have seemed like magic to Newton, but are now routine observations for modern astronomers. Until next time, keep looking up at that moon and remember that every time it tugs at our oceans, it's also pulling gently at every atom in your body, connecting you to the cosmic dance that began with the birth of the universe itself. Sleep well and dream of gravitational waves.